Okay, so far we covered regression trees, so decision trees that are used for regression. So let us do classification trees. So here is the data set. It is taken from a large survey in the United States. It is called How Couples Meet and Stay Together. The whole data set has 285 variables, but I have simplified it, so I have chosen 14 for this lecture. So we are going to predict marital status of this couple. So given all the observations on one couple, so basically this is the list of answers to a survey questions. And we are going to predict whether they are married or they are not married. I know that it's not very exciting to predict whether they are married or not married. It's probably much more exciting to predict, I don't know, at early stages of their relationship, if they're going to break up or if they're going to stay together. But I have tried to look into the data. I'm not sure whether it is possible, so I encourage you to explore the data further. But again, so we will just predict whether a couple is married or not married. So very simple. Okay, so here is a decision tree for classification. This is what it looks like. So it is basically very similar to a decision tree for regression. So only in the there are some subtle differences, right? So so one thing is that instead of deviance, we have this loss. For regression, deviance means residual sum of squares. So when we print a decision tree for classification, so what we have here is the number of misclassified nodes. So this diagram tells us that out of 2,796 nodes, if we made the split, if we do not make any split, so if we just predict everything with the most probable class, which is yes, so most couples there in the survey are married. If we just predict that everyone is married, then we are going to misclassify 923 nodes. So now, and so on, right? So we can check. While we are going down along the tree, we can see how many nodes are misclassified for each split, right? So then we have these decisions, right? And then we have probabilities. Now, probably it is a good idea to figure out whether it is the probability of no followed by probability of yes, or whether it is probability of yes followed by probability of no. So is it yes or no? So now let us just look at the root. So the root, the predicted label for the root is yes, and this should be the probability of the most probable class. And so it means that yes is the most probable class for the root, and therefore this is yes and this is no, right? So y probability is the vector of probabilities, so probability of no followed by probability of yes. For this particular data set, it just shows the order, so no, then yes. Okay, so same thing. So terminal nodes are that correspond to making decisions, so they are labeled by stars. And then we can, so given some new observation, so we can just go down along the tree and see how it is classified. Okay, now, so here is how it is plotted. So, and again, the plot is very similar. So one thing is that it reports three kind of things here in the terminal, well, in all the nodes. So the most probable label, right? So then the probability in this case, so notice that this is the probability of no, right? So what we see here is the most probable label, the predicted label. The probability of yes, not the probability of that label, because for no, it predicts 0.3. But if the probability of no were 0.3, then the predicted label would be yes, right? Not no. So this is how I know that it's the probability of yes always. And the third number here is the fraction of training observations that belong to that decision region, right? So this is the percentage of training observation. Okay, so let me explain a little bit about this decision. So the first split is sex frequency, and it may seem strange, but the reason is because sex frequency here is actually something like a categorical variable. It's not a number. So here 1 means something like they have sex every day. So 2 means something like they have sex, I don't know, a couple of times per week. I don't know, like every day. So 2 means like a few times, a couple of times a week. So then 3 is less frequent, and so on. So 6 means they do not have sex. Right, so it's kind of the sex frequency is kind of the inverse sex frequency, so to say, right? So what this first split tells us is that if sex frequency is bigger than or equal to 6, it means that they don't have sex. Then they're definitely not married. And this makes perfect sense, right? So if they do not have sex, then they are not married, and we can be 100% sure in that. And this is what this node tells us. Then the prediction is no, they are not married. The probability of this prediction is 1. So 1 minus 0 is 1, and 15% of all our observations belong to that node. Well, and so on. So you can check. So like age, if age is less than 32 versus if age is bigger than 32, and it's kind of if age is small, then probably no, is they are more likely not to be married. Or maybe it's better to look at this. Say if age is below 26, so if age is below 26, then they are more likely to not to be married. If age is above 26, they are more likely to be married, and so on. So this, what I want to say is that this decision tree makes perfect sense. So it is consistent with our common sense. Now we can prune it, right? So so this is the cross-validated error versus alpha. So remember that when we prune a tree, so we have this the residual sum of squares plus this regularization term, which is alpha times the number of terminal nodes. And in this case, it seems to be that alpha that leads to 8 terminal nodes is better than alpha that leads to 9 terminal nodes. So strictly speaking, one of these 9 terminal nodes, there are 9 terminal nodes here, it should be pruned out, right? So I'm not sure which one it is. I haven't really checked it, so probably, I don't know, maybe it's this node. And then if we prune this part, it means that this node becomes the new terminal node. Okay, I'm not sure which one it should be pruned out. I haven't checked, but my point is that regularization with pruning works in the same way for classification trees as it does for regression trees. So, and here is an alternative decision trees, an alternative decision tree with some categorical variables as predictors, right? So, by the way, so here religious means how often they go to a church, and this is kind of the inverse frequency, just like sex frequency. So if the answer is no, it means that they are actually religious. So often go to church. Often go to church. So basically it tells us is if they are religious, then they are more likely to be married, as opposed to if they are not religious. Okay. Now, what I want you to look at is this split, right? So according to the race. So there are 5 levels, 5 possible values for race. Others, I believe that this is America, so others is probably mostly Asian here, right? But what it tells us is that if the race is Black, Hispanic, or others, then we go to the left. If the others is not Black, Hispanic, or others, meaning that it's either white or mixed, then we go to the right. Okay, so why Black, Hispanic, and others are less likely to be married, I don't know. I guess it probably has to do with American culture. I cannot explain the display. Probably it makes sense. But this is what it looks like. So my point being is that if there is a categorical variable as a predictor, then the split is chosen so that some some values of the categorical variable go on to the left, some go to the right. And this is what it looks like. And again, so you can see this split according to the categorical variable here. So either it's Black, Hispanic, or others versus mix or white. Okay, so this was all about constructing a classification tree. Well, about how it makes its prediction. And so now please do this little quiz.